first thing we need to talk about is the exponential parent function. So that means what do these functions look like just in their basic form? And that's what's supposed to go in this little box right here under exponential parent function. And once my thing gets going, all right, it is y equals b to the x power. Okay, y equals b to the x power. Now, it's good that we use a b because that stands for the base. All right, and the exponent always has an x in it. That's what sets this apart from a polynomial. Polynomials have exponents too, but the exponents on a polynomial are always numbers. In an exponential function, your exponent is a variable. So, excuse me. If b is greater than 1, the function is an exponential growth. Okay, if b is greater than 1, then it's exponential growth and is increasing. Okay, and is increasing. And that's as you go from left to right. All right, left to right, it is increasing. If b is less than 1, now be careful, don't just say that b is a fraction, because there are fractions that are greater than 1. 3 over 2 is greater than 1. But if b is less than 1, the function is an exponential decay. And exponential decay is decreasing. Kind of makes sense. The d's go together. Decreasing, decay. Okay. These will have an asymptote. They have a horizontal asymptote, kind of like with our rational functions. For the parent function, it is always y equals 0, or the x-axis. Okay, these functions, these exponential functions, in the form b to the x will never cross the x-axis. Now, we will get to some where we're moving them, we're shifting it up and down or left and right, and they can cross the x-axis. But if it's just b to the x, it's never going to cross the x-axis. All right, so we're going to look at a few of these, and we're going to classify them as growth or decay. We're going to graph it, and then we're going to talk about some of its key characteristics. Okay, so what I need you to do is I need you to plug y equals 2 to the x into your calculator. Okay, everybody needs to put y equals 2 to the x in their calculator just like this. Okay? The exponent button is right above your division symbol. All right, so 2 to the x, according to what we just wrote down a second ago, is that growth or decay? Is that exponential growth or decay? Growth, okay, because the base is greater than 1. So this is exponential growth. So I haven't even looked at my graph yet, but I expect it to be an increasing function. And so let's look at that graph now. Here we go. All right, click graph. This is what our exponential functions look like. They appear to just kind of come out of nowhere, but that's not really the case. They get really close to the x-axis over here on the left. But something that we do need to be aware of is where it crosses the y-axis. So if we go to the table and we look at where x is 0, then our y value is 1. And while we're at the table, we might as well get a few other values here. 1, 2, 2, 4, 3, 8. And then 4, 16 would be off of our graph. We can go over to our negative values. -1 is 0.5. And then look what starts to happen to our y values. Very, very quickly, they start getting very, very small over there on the left side. So this is what our exponential function looks like. Like I said, it doesn't just disappear over there on the left side. It just gets really, really, really close to the x-axis. So if you can express that on your graph, that would be great. And notice how rapidly it grows. Okay, I said at 4, the y value was already off of our graph. That typically doesn't happen with our functions, polynomials, and things like that. Exponential functions grow very, very quickly. Okay, that's something about exponential growth and decay. It happens very, very rapidly. Now, let's fill out these key characteristics that we've got over here on the right side. The domain of an exponential function is always all real numbers. Okay, it's always all real numbers because we can raise any number to any power and we get an answer. You can raise it to negative powers, you can raise it to positive powers, you can raise it to the 0 power, you can raise it to a fraction, a decimal. It doesn't matter, you're always going to get an answer. So the domain is all real numbers. The range is not all real numbers. Okay, the range is talking about our y values. Do we hit any negative y values there on that graph? No, we don't. So all of our y values are greater than or equal to 0. Okay, let's talk about end behavior. End behavior, they love end behavior in Math 3. We've talked about it with our polynomials. Let's look at it here with our exponentials. As x approaches positive infinity, that's the right side over here. This is positive infinity, this is negative infinity. So as we go over to the right side, where are our y values going? They're going to positive infinity. They're going up, 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 up very, very quickly. So f of x, or your y values, are going to positive infinity on the right side. As our x values approach negative infinity over here to the left, what are the y values doing? Where are they hanging out? They're hanging out at 0. Okay, they're not equaling 0, but they're getting really, 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 really close to 0 over there. The y-intercept, we already talked about it when we first graphed it. It's 0, 1. Okay, and our asymptote here is y equals 0. We already talked about that. That's true. As long as it's just b to the x, we don't add or subtract anything there, the asymptote's always going to be y equals 0. Okay, so let's look at example number 2. Okay, 3 to the x. Whoops, too far. 3 to the x. Exponential growth or decay? Growth. Okay, exponential growth because the base is greater than 1. Greater growth. Okay, connect those two things. Greater growth. Decay is decreasing. All right, so let's graph this and let's see how it's different. I'm going to leave 2 to the x in there because I want us to kind of compare the two. All right, so I'm going to leave 2 to the x in there. I'm going to also put 3 to the x in there. And let me show you something that you can do with the calculator that can help you distinguish between two things that you have graphed. Have you ever wondered what those slashes beside the y1 and y2 and stuff were? You may have, you may not. You may not have paid attention home at all. But you can actually move your cursor over there. You can use your left arrow to move it over there. And when you press enter, that line is going to change. The first thing that it changes to is a darker, bolder line. So that means when we graph these, look at what happens. There was the first one that I graphed, and then there's 3 to the x. It just made it a darker, bolder line so I can see the difference between the two. Okay, and I don't have to remember, well, which one showed up first, which one showed up second. Okay, so that's what 3 to the x looks like. Now, because I made it a bolder line, it kind of looks like it goes below the y-axis here. Let's look at the table and see if that's actually the case. All right, I'm looking at the values in y2. So I've got 0, 1 still. Even though the function changed, I still have that same y-intercept. 1, 3 is my next point. Then I've got 2, 9. And then I'm already off of my graph when I get to x equals 3. So that grew a little bit faster than the first one. Negative 1 is 1/3 or 0.3. And then notice these y values get even smaller, even faster than the first one did. Now I'm looking to see if any of them end up being negative. Now these are not negative numbers. Remember that E is scientific notation. That just means they're really small, tiny numbers, okay? So I don't actually go below the y-axis like it looks like I do because I use the darker, bolder line. I just get smaller faster over there on the left side, and I get bigger faster over here on the right side. Okay, so same general shape, it's just a little bit steeper, the growth is a little bit faster. Okay, the domain is still going to be all real numbers. I can raise 3 to any power, I'm always going to get an answer. That is always the domain of an exponential function. Polynomials and exponentials, they're always all real numbers. Okay, the range is also the same right here. Okay, the range is y is greater than or equal to 0 because I still don't hit any negative y values. All my y values are above the x-axis. Okay, my end behavior, does it change from the first one? No, the graph looks exactly the same. So as my x values are going to the right over here, my y values are also going to positive infinity. And as my x values are going to the left, then my y values are still leveling off at 0. My y-intercept is the same, and my asymptote is the same. Okay, so some of these characteristics, they really share, even though it's technically a different function. Okay. Okay, let's look at number 3. Okay, what changes about number 3? I'm sorry? It's a fraction, okay, but more specifically, it's less than 1. Okay, it's less than 1, so is this still exponential growth? No, it's exponential decay. It's exponential decay. Go ahead, Ivy. Okay, so let's go in now. The original problem has parentheses. You've got to put parentheses in your calculator when you type it in. You can't just leave those parentheses off. If you do, it's just going to apply that exponent to the 2 that's in the denominator. It's not going to apply it to the 1/2. So you've got to put parentheses around that fraction right there. Okay, let's graph it and see what it looks like. We said that it was supposed to be decreasing. So look at the shape. It's very similar to the shape of the other ones, but instead of increasing as we move from left to right, it is decreasing from left to right. So let's get some y values here. Now, I need to go the other way to get some y values that I can grab. At -3, the y value is 8. And at -2, it is 4. And at -1, it is 2. Guess what it still is at 0? It's still 1. Because anything raised to the 0 power is 1. At 1, it's equal to 1/2. At 2, it's equal to 0.25. Are these y values sounding a little familiar to anybody? They're kind of the same thing as 2 to the x. They're just opposite. They're flipped. Okay. That's an interesting property of our exponential functions. Okay, so we can fill in our graph right here. So same shape, just flipped around. The domain is still all real numbers. Has the range changed? Have our y values changed? Not really, they're just flipped around. We still don't get any negative y values. Oh, those should not have equal to's. I am so sorry. It's greater than. It's not equal to. It should just be y is greater than. My bad. Change all those to just y is greater than 0. Not equal to. Don't know what I was thinking. Monday morning, right? Just y is greater than for all of them that we've done so far. Y is greater than 0. I even said we can't equal 0, and then I still wrote it. Okay, in behavior, okay, as x approaches positive infinity, the right side over here, where are our y values going? They're going to 0 this time, okay? As we go to the left, as our x values are approaching negative infinity, where are our y values headed? Up, right? They're going to positive infinity. So that relationship just flip-flopped. We flipped our graph around so that in behavior relationship flips. Our y-intercept is still 0, 1. Our asymptote is still y equals 0. Okay. Okay, let's look at 2 more here, right? Yep, 4 and 5. Okay, number 4, exponential growth or decay? Decay, 2/3 is less than 1. Okay, 2/3 is less than 1. So let's just go with some of the things that we've known so far. Our y-intercept has always been 0, 1. When we plug 0 in, 2/3 to the 0 is 1. Anything to the 0 power is 1. I know this is going to be decreasing. I do want to get some specific values. So I am going to plug this into my calculator. 2/3. Go to my table. Okay. So at -4, we're at just above 5. 2, 4, 5. Just above it right there. At -3, we're just below 4. Well, actually, just below 3.5. -2, we're at 2.25. -1, we're at 1.5. At 0, we're at 1. At 1, we're at 0.7. 2, we're at 0.4. Okay, so what's a little bit different about this one? Is the growth as drastic, or is the decay as drastic here? At -5, we're at 7.6. 2, 4. Okay, how does this graph compare to the other ones that we've been graphing? Is it about the same? Anything different about it? If we look at it on the calculator, it's not as steep, is it? It's a little bit more spread out. I was able to go all the way to what, -5 and plot a point. I haven't been able to get all the way to a 5 yet, negative or positive, and for it to be able to fit on the graph that I've got. So this 2/3, it kind of spreads things out a little bit. Okay, domain, still all real numbers. Range, still greater than 0. The end behavior, it's the same as number 3. As we go to the right, as our x values approach positive infinity, our y values are going to 0. As we go to the left, as x approaches negative infinity, our y values are going up to positive infinity. Our y-intercept is still the same. Our asymptote at y equals 0 is still the same. Why are we writing this over and over again? Because maybe, hopefully, it will stick if we write it enough. Okay, one more. Number 5. Okay, so we have a fraction, but is it decay? No, it's growth. Because 5 halves is equal to what? 2.5. 2.5 is bigger than 1. Okay, so you got to be careful. It's not just if it's a fraction that it's decay. That fraction has to be smaller than 1. So let's put this in so we can graph it. 5 over 2. Go to the table. Oh, let's see here. -1, we're at 0.4. 0, 1, still the same. 1, 2.5. 2, 6.25. 2, 4, 6.25. And at 3, I'm already out or off of my window. So this is all that I can accurately graph, I guess you'd say, without typing in some decimal values. Okay, so this is the steepest, well, it's not the steepest one yet. 3 was a little bit steeper. But what I want you to see is the bigger that base gets, the steeper this graph is going to get. The smaller the base gets, the less steep it's going to get. So the domain's still all real numbers, range, the y values are still bigger than 0, they're always positive. The right side of this, the y values are going to positive infinity, the left side they're going to 0. Our y-intercept's still the same, and our asymptote is still the same.